Hey, everybody. Good to see you all. I am Duffy Cooley, and I am hosting episode 16 of the eCHO, EBPF, and Cilium office hours. So today's episode, I'm going to do a continuation of kubectl-trace. We're going to dig a bit more into it. I've learned a lot since the last one, which was, I think, something like 3 or 4 weeks ago. I've learned a lot about how to make eBPF data available within the Linux kernel. And I'm going to talk a little bit about that in this session. And I'm also going to, and then we're going to dig into it and play with some of this tooling and see what we can learn and that kind of stuff. So before we get started, let's say hello to our awesome audience. Good to see you, Noel. Good to see you, Khalid. Glad you're here. Anybody else want to say hi? Just feel free to jump into the chat, say hello, and I can actually raise you up here in the comments. But good to see you both. I'm hoping that we get that there's a bunch more people watching and enjoying the thing. We got about 5 viewers so far. Remember that you can always click that subscribe button on the bottom, and then you'll be notified whenever we're going to do another episode or anything else like that. Let's get into the news. One doesn't work. There we go. That's better. All right. Can somebody give me a thumbs up on sound? You guys can hear me and see me and all that good stuff is working well. Hello, Nick. Hello, Nick in Chicago. Good to see you, sir. All right. So this week's news, I have a link to the previous episode so that if you haven't watched that previous one, feel free to watch me fumble around. I learned some interesting things. What I was trying to do in the last episode was play with kubectl-trace, and I realized that for a lot of the BPF programs to work, there is some type information that needs to be made available to the BPF program itself. And weirdly enough, this type information is called BTF. So there's BPF, Berkeley Packet Folder, and then there's BTF, Berkeley Type. Apparently, these are the types that your BPF programs need to be able to provide some of the context for what's actually happening in the kernel events. So we're going to play with that a little bit. And actually, one of the articles that I wanted to share with you today kind of talks about that. So I haven't had time to look at this one ahead of time, but I'm sure we'll play with that a little bit. One of the things that happened this week is a tech podcast. If you're interested in this, there's a tech podcast put out by Form 3, and they just did a great episode on Cilium. So just an incredible episode talking about like what they do with Cilium in their clusters and kind of digging into like why Cilium is such an interesting product from that perspective. The next one up is the one that I was actually talking about, which is this simple eBPF Core application. And Core is the thing I'm talking about. And what that means, this is the ability to embed into the Linux kernel the BPF types so that you can just have portable BPF programs. And I'm gonna show that when we play with it a little bit. And we're not quite there yet, but when we get there, it'll be pretty fun. But continuing the series with EPBF development ecosystem and a step-by-step guide for writing a simple application. So if you're interested in digging more into ePBF and experimenting with it, this article seems like a pretty good place to start. Talking about generating bytecode. Once you actually do a load of that bytecode into the Linux kernel, it goes to the verifier, which we talked about a bit. Per output gives us per event data, and then we can take the data that we've learned or the context that we've learned about this application, kick it to a map, and then expose that, and then pull those maps down into statistics. If you tune in 2 weeks, I'm actually going to be joined with Chris Nova, and we're going on the next eCHO episode that I host, and we're going to be digging into an application that Chris has been working on called the double slit experiment, which is kind of a fun physics thing where like observing a system inherently changes a system. And so we'll be talking about that. Hello, Avian, good. Thank you very much. Hello, Russell. Good to see you. Noel has a quick non-echo question. What's the audio setup you're using on Linux? Couldn't find much good info. I'm using a Spark. I'm using a Blue Spark microphone, and I'm just using it as an audio source. I think right now I'm using Pulse Audio or something like that, if I remember correctly. But it seems to work. Hey Rico, good to see you. Yeah, double sit should be fun. If you haven't checked it out, it's a fun project. It's up in Chris's repo. But basically, its intention is to capture some information about applications that have been put up. So this talks about once eBPF was introduced into the kernel, Linux developers, which tool is perf, IPRoute, and libbpf, implemented slightly different BPF loaders based on the BPF2 system call. This post will cover libbpf because it's the most generic solution and served as the foundation for the BPF Core project. The libbpf-c library provides a collection of functions that enable easy, and this is actually where we talked about helpers and user space loaders and that sort of stuff that actually really help kind of develop, think of it like a framework for developing BPF programs. We talked about BCC a little bit. I think I want to get into, there we go, BPF Core. So compile once, run everywhere. That's what CORE is standing for in this case. Has been in development for a while and was finally added to libbpf last year to solve the aforementioned portability issues, right? Which is where you have to actually make that BTF or BPF type information available, and it would be changed. Memory layout and data structure definitions change between different kernel versions, between different architectures, and even between different builds of the same version. Moreover, kernel structs have their own fields removed and renamed. The common way to deal with that was to have multiple BPF programs with conditionally defined struct access code based on the kernel configuration from which the program was built. So what that means is like you would grab the type program information and make that available to your application on compilation, right? So as you're actually building this stuff, you need to make sure that you have that type that type stuff available. BTF deduplication. The extensions to CLang and libbpf work similarly to the way classic executable loaders work. CLang extensions add BPF relocations to the generated BPF elf file to describe what kernel data various parts of the program are trying to access. The libbpf library then acts as a loader and processes that relocation data when loading and setting up the BPF program in maps. Let's talk about what that means like on a practical basis. So practically what that means, it's actually kind of an interesting thing. So ls sys kernel BTF VM Linux. So this is where the type information for the kernel that I'm running is held, and the way that this is actually created is through a kernel configuration line. Let's just go ahead and look at that. Grab config debug info BTF config. This kernel configuration parameter, if you're going to build your own kernel, which I'm probably not going to get into in this episode, but if you did decide to build your own kernel or you wanted to use a kernel that already makes this available, of which there are quite a few, Ubuntu already does it, Red Hat already does it, Arch Linux on the LTS kernel already does it, then you wouldn't need to build your own kernel for this. But once you have this file, syskernel BTF VM Linux, then the type information or the mapping of those calls is then made available kind of automatically within the Linux kernel construct. And then when you're actually compiling the application that you're going to inject, that type information can be learned or referenced from this from the output of this, or from this particular BTF output, because all of the struct data and all that stuff is all right inside of this piece. But if that's not available, then we have to provide that data some other way. And there have been a couple of different ways to do that. Let's see if I can find one for you. So this was the mechanism that I was using to actually build this more dynamically, right? So we can do things like grab from a built kernel that has that debug command line on. We can actually grab the. I'll answer that question in just a second. Hey, Lorenzo, good to see you. We have Lorenzo joining us. And Noel has a question, which I'm going to come back to in just a second. What's in proc configgz, and does that show up in proc command line? So great question. What's in config.gz is the actual kernel config that was used to compile that particular kernel. So the one you're running, it basically copies the .config that you would use when you were doing like a make on the Linux kernel into a gzip file and makes it available inside of the proc file system. So you can do things like look at the configuration of that Linux kernel that you're running and see what that state is. Not every implementation, every build of the Linux kernel has this, but it is a feature that you can turn on or you can enable or disable. And it has nothing to do with the command line itself. This is more like what were the bits that were what was the configuration file that was used when this kernel was compiled. And so you can see how that would be useful. Awesome. So let's just go ahead and run this. Well, we can't run this command right now because I don't have the debug kernel. But if you do have a debug, like if you were to grab the debug, this is very strange. I'm starting to see kind of things kind of come and go a little bit here. We'll see if that actually mellows out. If you do have that data, if you do have a debug kernel, then you can use commands like this one, llvm copy, and then grab the BTF section itself and kind of like pull all of those structs from that debug kernel into one file, and then make that file available to your BPF programs or to your libbpf-based programs by providing it as an argument. But if it's made available inside of your Linux kernel, then you can kind of get that automatically or kind of programmatically for free using libbpf. And that's what the point of this article was, that portability piece. So when you say, Russell, when you say that libbtf VM Linux is available for you, what Linux distribution are you running? So they get into developing a simple BPF Core application, and they kind of talk about exactly that piece I was talking about. What are the kernel config options that you would need to see to make sure that we could even do this, right? Building the kernel with these options makes the binary BTF available, BTF info available in syskernel BTF VM Linux, which we just talked about. And later on, we will use this binary BTF information to generate the vmlinux.h header, which replaces the old kernel headers that users had to include. So we can start by writing a BPF program that first attaches to the execv system call. The usual convention is to add bpf.c postfix to such files. A starting example looks like this. So loading the helpers, attaching to the system call, entering any execv. So anytime you're going to run an application, and then we return 0. First line includes the vmlinux h.header generated from. At this point, we can go ahead and generate that file. So this is an interesting line. Let's go ahead and take a look at that. I feel like this should be more automated than it is, but we'll talk about why I feel that way in just a second. So the command I just ran, boop, 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 boop. Let's just jump back to the top here. Wow, that's a lot of data. This takes the type information that is related to my specific kernel that I'm running. It's taking the file. let's just look at the command itself. So what I'm going to use is I'm going to use BPF tool. I'm targeting the BTF sub part of BTF tool, and then I want to dump the file that is located at syskernel BTF VM Linux, and that's where all of my BPF structs are held. But I want to dump it into a format of format C. And actually, before we even do this, let's just look at a help command output here and see what else we can actually do. So there's two outputs. There's raw and C. And raw just basically gives us the mapping of kind of where in the kernel these structs are located, so that we can understand what's actually being used and sort of map these things back to. Think of this a little bit like debug data, right? Like we want to make it so that when we see particular things being called, we have some reference back to like what the actual call was and like that sort of stuff. So there's a spin lock, dir context, poll table struct, VM area struct, an inode struct, file lock. Some of these are going to be system calls, and it's going to basically provide. This gives us a way to kind of have a lookup table for understanding. Oh, nice, got it. Red Hat, I assume, but it sort of gives us a lookup table so that when we're actually getting event data back out of the kernel, we have a way of understanding like what contextually we're talking about here, right? And so, for example, if we look at that BPF program that we saw in the example in the document, right here, we're saying that I want to target syscall enter exec VE. And so we need to have some way of understanding, like, because at the system call layer, like that's a number. It's not even like, it's not titled that way. So these helpers need to have some way of actually understanding how to connect the pieces so that you actually get a reasonable program, and we have some way of actually outputting that. So one advantage of Core is that this file rarely has to be regenerated, as libbpf will adjust the program with regards to any kernel differences during load time, thus the name compile once and run everywhere. However, if we were to cross-compile this for a non-86 architecture, we would most likely need another VMLink header generated on a system with a matching architecture. So this is where I feel like, I mean, I can understand that we're making a portable file, a vmlinux.h. That header file will now be portable. We could package it with this binary that we're building, or with this bytecode that we're building, and ship it all together. And it could even be statically compiled into that bytecode, so that you could just load the bytecode into any system that is an x86 based system. But one of the things I was surprised by, and I feel like I have the right person to invite on this show to ask him this particular question, is like, why not make it so that libbpf would evaluate whether this file was present, and if it is present, then just load the details from that struct at compile time, rather than having us provide a header file for it, right? Like this step seems, I can see the value of portability, but I'm not sure yet whether it's the right thing. Whether I'm overthinking it, or whether it also makes sense to make it so that you could just have that guarantee of portability, ship the VM-Linux header. But if there is a VM-Linux header struct inside of the Linux kernel made available in sysfs, then maybe use that one. And that would kind of give us even a little bit more portability, but I don't know. In my head, that's what I'm thinking about. So lots of good stuff in this article. I kind of want to move past this article because there's a lot more that I want to cover in this episode, but I just wanted to share with you kind of what I saw and what I thought was kind of interesting. But they have some great examples for generating a skeleton program, for giving, for kind of building your first like non-trivial example, for how all of this works. So maybe in some future episode, I'll come back to this article and we'll just work through it. I think that would be kind of fun. But that day is not this day. So let's keep going. There's a Rust crate that simplifies the integration of Rust and EBF programs written in C. I'm curious about what the goal of this one is. This crate simplifies, yes, cargo build system, build RS. Also embed ELF files as lazy, statically loaded U8 slices that can then be executed directly from memory. That's also pretty neat. So if you're into Rust or you're playing with Rust and BPF, this seems like kind of a neat thing. I wasn't aware of this, but it looks like it's just using the Rust tool chain to actually give you some mechanisms for compiling BPF programs. One of the other projects that's out there, defining the first trace points in documentation on user space, statically defined tracing. So pretty cool articles, kind of referencing some of the better known articles that are out there from Collabora and Brendan Gregg's blog post talking about BPF. So doing this tracing in eBPF, very cool. Understanding the different trace points. So this is actually using eBPF to introspect what's actually happening on a syscall level and an application level for a given user space application. So like Bitcoin D, like these trace points have been defined here, and we can actually understand like how many times a particular code path was exercised, like how long it took to do those sorts of things. They're looking for the 3 trace points that they're targeting are inbound message, outbound message, and block connected. Validation, block connected. And so that's actually pretty neat. This is an example of leveraging BPF to do like application layer tracing. Pretty cool stuff. It's neat that they're kind of developing this internally. I know that there's some tooling out there that kind of digs into this in a more generic way. I'm curious if they've evaluated that, but looks like it's on its way. The last article I have for you is Sysmon for Linux is coming along nicely. eBPF for the win. What's happening here? Oh, cool. So moving Sysmon to eBPF. So you can actually get events that have a lot more context about what's happening because they're gathering that context from the Linux kernel. I hadn't actually seen that this was a thing yet. That's very cool. So like, retooling some of the old tools that we have into using some of the newer technologies that we have available to us. Pretty cool. So I was not aware of that one. All right. Let's get started with kubekiddle. So kubectl-trace is hosted inside of the IOVisor project. Noel has asked a question. Any reference to CVE 2021-3490 today? I think. Let me take a look at that one. I don't have anything prepared for it. So hellobalance bitwise, Linux kernel does not properly update 32 bounds, which could be turned into an out of bounds reads and writes in the Linux kernel, and therefore arbitrary code execution. This was fixed in 513 RC4 and backported into the stable kernels. Oh, nice. So the verifier was missing something. Nice. I mean, it's good that we have the verifier there to actually like do some of these, to do as much validation as it can. But that's a nice catch. But it looks like it's been patched, so as long as you're on a recent kernel, you should be okay. I don't know too much about this one. That's a fun one. Perhaps we can cover that in a future episode. But it'd be kind of fun to like do an episode where we kind of dig into some of these CVEs and show like how the exploitation process would work. But cool stuff. Apparently, thank you for that reference, Noel. So where I started last time was I brought up a Kubernetes. I think it was just a regular kind cluster. Oh yeah, give me a link for that. I'd love to dig into that. You can actually put that link into the notes, and the link for the notes is right down here where it says show notes. If you go to hackmd.io/@echolive, you can find a link to the notes there. Just drop it into a reference, and I can dig into it from that perspective. I probably want to read it and dig into it then, but yeah, that'd be a fun one. So coming back to what we were working on. So last time when I was working on this stuff, what I ran into was I think I brought up a minicube. I brought up a minicube multi-node cluster, and I ran. I was trying to work through some of the examples, and I ran quickly afoul of the fact that minikube did not have the BPF bits available inside of the kernel. So we can actually prove that out. So knowing what we know now, or having learned what we have learned, let's do this. Let's do minikube start. And we should be able to see some interesting output here. But yeah, last time when I tried to do any of the kubectl traces, they failed for me because I didn't have the BTF type program stuff available. And so there was no way for it to evaluate that stuff. But hopefully this time I do have it. I'm actually going to try running some of that stuff in a kind cluster, like a single node kind cluster, because that kind cluster will share a Linux kernel with one that already has that BPF program. And so while this is coming up, I'll go ahead and I'll show you what I mean there. So if I do, ls sysfs kernel btf vm linux, that's there. And then if I do docker run it bash into bash here. Oh, look at that. Oh yeah, it's there. Thank you, Noel. So hopefully that means that I can bring up a single node cluster and we can get a little further with our experiments, because last time we kind of got shut down like before we even got started. So I'm gonna minikube SSH, and then I'm gonna do ls sys kernel. And we can see that in minikube, that content is not available, and so we weren't able to actually do any work there, and that was what was I think causing our problem. But we'll see. I'm gonna go ahead and delete this minikube cluster. It's a little bigger. We'll do kind create cluster. So we already have, and if you want to see how that was done, we already have kubectl-trace installed. All of that stuff is already in place. So the stuff I wanted to start playing with is this usage stuff. And this is where I ran into trouble last time, was that the very first thing I ran was unable to actually get it done for me. And so I kind of wanted to get into it a little bit more. So I'm going to grab this right here. And then we can kind of play with the different programs and see what we see. And try this out. So we have our kind cluster up. I'm going to do kubekettle -a. Still coming up here. Just watch for a sec. While things work themselves out. Almost there, waiting for core DNS and local path storage to hit. And there we go. All right, we're all up and running. So for our next trick, we're going to go ahead and grab this piece, which is looking for sysenter syscalls, and we're going to count how many there are. So let's try this out. But because the node is going to be different, right? We don't have IP 180, whatever. What we do have is kind control plane. We're going to do kubectl-trace, run kind control plane, -e, trace point syscalls sysenter. We're going to do the at probe here, and then see a count of those, or that's going to be the probe that we're going to hit. And if we do kubekettle get jobs, like we did last time, we can see that trace happening. We'll see what happens from the completions perspective here. All right. If your program has maps to print, use sending a sigint using Control-C. If you want to interrupt the execution, send sigint multiple times. The last time we ran this, in fact, you know what? Let's just show what that looked like last time we ran it, because I think that would be more useful. So let's do minikube start again. But we didn't even get to like attaching 336 probes. It got nowhere nearly for that. Get this guy booted up here. Kubekiddle. KNS. So we are going to run the same command. Nope. There's one of those. So we'll do kubekettle get nodes. I forget what the node name is. It is just minikube. All right. So while that's working itself out, I'm going to do KNS CTX kind. Pods. Still running, and then kubekettle get jobs. Completions. So I guess what I want to do, let's see here. Kubekettle This is the PID namespace. We talked a little bit about how this is laid out last time, and I'm probably going to cover it again here. But like this is running. This is basically when I provided that node name, I guarantee that this application would run there, and then we're seeing the process in particular that is running should be here. There's our trace runner. So I want to do a kill -hup of 1991. Seems like a good year to help. Kubekiddle get, kubekiddle get pods. What are my options in kubectl-trace? What I'm running into here is I was trying to figure out how to actually end the trace so I could see the results of that trace. I'm not seeing exactly how to do that. Kubectl-trace get. All right, and then logs. No logs to be seen. Let's try attach. I wonder if there is something in our docs that will give me a place to start here, because I've been able to get the thing successfully deployed, but okay, CTX minicube. Get pods. Oops. Weird. Okay, maybe the context switched on me right before I was trying to run it. So let's try running it again. Window 1 of completion. Did you see how that completed right away? Oh, and then it deleted itself. Pods. Hit all events. Events. Wow, that's fun. So something must be aggressively cleaning these up, because my trace did get created, but then it got deleted almost immediately. So, which is different behavior than I saw last time. Yeah, yes. Yes. Wow, it's like it's even gone from the file system. Fascinating stuff. I wonder what's happening there. All right, let's dig in here. Let's see if we can figure this out. So this is the layout we were talking about before, where you can actually specify a node name, and it can attach ret probes and trace points and other profile events like directly against the nodes if you specify the node name. And then the way they're doing that is through affinity. And that I thought was a pretty clever way of doing it. So if I do kubekiddle, describe, actually get x kind. So when you specify a node name, like we did, I thought there are a couple different ways that this could be done, right? This could be done just by populating the node name field directly in the manifest. And that is right here. And probably a more, maybe a slightly better way of handling that would be to pre-stop, interesting, would be to do that with node affinity, which is this piece here in the manifest, right? So when I specified the node name, it did node affinity, or it configured node affinity on that job to make certain that trace runner would run exactly on that one node. So if you had multiple nodes or something, you could target a given node for a particular trace. You could run like different BPF programs against that node and then see the output. So there we are. We see that here. Well, it's going to run for 3 minutes. There we go. Now we're getting somewhere. So that was actually how they configured it, which I thought was pretty clever, because in some situations, there would be an admission policy that doesn't allow you to define things like node name. But as you can imagine, it's also getting that host PID, and that's why when we exec in and we did PS, we saw all the processes, and which is, it makes sense, right? We have to inject these BPF programs kind of as a privilege in a privileged way to be able to get the sort of context that we need from the Linux kernel directly for most of these things. Now, there are some programs that we probably wouldn't need that level of privilege for, but in this particular context, we would definitely need that kind of level of permission. It's been running for 11 minutes, so the timeout thing doesn't seem to be real. Do kubectl trace. Get delete. I'll get jobs. Get pods. I'm not sure what I'm missing here, but maybe there's, like I said, in the documentation, a better way of understanding how to send that control C, because that part's not entirely clear to me. We go through some service account stuff. Now that we have kubectl-trace, we can do pod security policies. Okay, now that we're all set, we can just run the program by specifying the service account. And if you have a different namespace, using patch to patch a job. If you wanted to modify the chain, or you wanted to modify it. So those are all of the different BPF trace programs that are kind of precompiled. What I'm looking for is in the example, I can certainly run the trace. I'm looking for a way to understand how to see the results of that trace. I'm missing something here. Oh, -A. Right? But how do you send to Control-C in a daemonized process? I can't, like when I exec in, all I'm Control-C'ing is the bash that I'm connected to. So I think what I missed was this -A piece, because apparently that means attach, and then it's a foreground process. So then I'd be able to see the content. So let's go ahead and try that again against the kind cluster. Then maybe we can run a we can play with the other tools. So -A. So this is, I think, what I missed. And I didn't see it in the document. And I think I just copied the whole line in this example line here. Because what I'm running into, basically, is that in this example, it's telling us how to go ahead and start a trace, but I have no way, I don't think, of getting the results of what I've learned from that trace. And so I'm trying to see how that works. If I do a -A, I think that means to attach to it, and then we'll be able to see that the trace is running. So kubekettle trace get, you can see it running. And if we do kubekettle trace logs, I wonder if it'll just default, it doesn't, to the name of our trace. See 336 probes attached. We're sitting here. Now if I hit Control-C, what happens? Oh, it just breaks me. I'm not sure how to get that data out. Logs. Oh, it says send a SIGINT. Okay, let's try that. I know how to do that. So kubekettle pods exec ti. Grep runner. Kill -I help. Signal. Okay, so we'll do pkill runner -I. -I, isn't it? Oh, -sig. Still running. Get all logs. Against received. Now, if your program had maps and did not free them, it should print them out. So that did work. Wow, super aggressive cleanup. This is really interesting. So when you interrupt the trace just gets completely removed from the world. There's nothing remaining of it. And I really do wonder how that's happening. That's pretty neat. Like there must be some semantic here where, like I know that Kubernetes garbage collection can happen pretty fast and it can be very aggressive, but I'm surprised that it's just completely wiped out, like almost immediately. Interesting stuff. All right, let's move on here. I am going to run a different example here. And I have some of this stuff checked out locally, and I've played a little bit, kind of proving out my particular content works. And so I wanted to play with that a little bit. So let's go ahead and jump over to number 4 again. We're going to play with a little bit of BPF programs like absolutely locally on my laptop without any Kubernetes involved. And then we're going to try and run that same program against the kind node that we have compiled. So let's see what we can get from that perspective. So let's do git, it's not iOvisor, BPF-trace. So inside of here, which is the iOvisor BPF-trace repository, and this is the link here. And if you were in the kubectl trace programs, it links you here. So inside of BPF-trace tools, there's a bunch of decent examples of tools that that show you stuff, right? And so like they kind of give you an example. Here's an example of like the capabilities set for individual processes or things that have run. And then here's the BPF program that actually does that stuff. I think that was a different, oh, that was CPU walk. Okay, I'm like, that doesn't look anything like what we were just looking at. So talking about the different capabilities, doing a kernel probe, and then capturing the process and the capability associated with it. So this is an example of a BPF-trace program. So let's go ahead and try and run this program and see what that looks like locally without any Kubernetes involved. And then we can try running that same program inside of the Kubernetes cluster, leveraging kubectl-trace. So BPF-trace. Let's do the capabilities one. There we go. We're getting some interesting output. So we can see kubelet output. We can see capabilities associated with different processes. We can see Xorg is running as capsysadmin. Pulse Audio is making a few different capability calls: set UID, set GID, sysnice. Kubelet, of course, has got a lot going on. If I were looking at this as a system administrator, this would make me kind of nervous, because a sysadmin is a pretty high level of capability. But digging into capabilities is kind of an interesting one. So we know we have output from that perspective, just running it locally on our machine. So let's try doing the same file, but against our target that we saw before, and see if we see different output from that perspective. I think that's the right syntax. Looks like the trace has been created. No output yet. It all logs. Ah, look at that. Interesting. So this is working. We can actually see, like, if you have a BPF-based program that is that provides output locally, then you can absolutely run this against another node. Should we try it against minikube and see what that looks like? I'm going to go ahead and delete this job. Pods. ACTX. Minikube. Now I'm on the minikube cluster. I should see this fail. But let's try it anyway. Oh, wrong node. Last time we actually got a reason why it failed. Oh, that's actually working. I wonder if because it's a kernel probe, so it's not actually leveraging any BTF programs. That's neat though. But look at how much stuff is running with capsysadmin here. That is neat. It's actually curious. I'm curious. What this does is it creates a container, and it gives us basically access to the underlying node, right? And so now I can do, say, sudo cat the password. So there's cat jumping in as sysadmin because I'm running as a privileged container. Neat. Capch. Capch. What I'm doing here is I'm grabbing the am I contained binary from a place where I have it stashed, and it gives me the ability to run am I contained, kind of see what permissions I'm getting. Whole bunch of it ran and then exited. I forgot that it does that. So we're in the We don't have a PID or user namespace, AppArmor profile, kernel, bounding. These are all the permissions that I have. That was nice. So I'm surprised that works for us, but let's dig in a little bit more. Let's see some other examples. So let's do delete job for that guy, kubekiddle get pods. That's not terminating. And then in our tools, I'm trying to think of an example in here that gives, let's see, grep -ir kprobe star.bt. Let's try this loads one. That should be kind of fun. See y'all later. Thank you very much for coming. Ooh, interesting. So load averages of 0. That seems kind of funky. Now we're getting somewhere with it. We do minicube h load uptime. So in this case, we're getting a false output. And interestingly, I wonder if that's because the probes are not successfully attaching because they don't have context. So let's try running that against our known good cluster. Let's see if we see a different output here. So I'm going to break that. Go ahead and delete that job. Do kctx kind. I'll run that same trace again with the right hosts, of course. Full plane. Ah. There is an example. So in this particular example, what I was trying to show was the difference between being able to determine whether like particular syscalls are being made available to the trace that's being run, right? And so when we ran against minikube, where there is no BTF type information, it wasn't able to detect the system load. When we ran against kind, which is actually got the VM Linux maps loaded up, then it was able to actually do that stuff. So pretty neat. You can also see the system load I have running locally here is, it's using up some CPUs. And of course, another thing we can kind of do here, which I think might be interesting, is we can do sudo EPBF loads.pt. And we can see that because in our kubekettle example, or in our kind example, we're running against this exact same Linux kernel. So we're seeing exactly the same output in the two evaluations, right? Whether we run it locally or whether we run it inside of a container, inside of another container, we're still seeing the same output, which is pretty neat. Yeah, that's cool. All right. Well, we are off to a running start with this series. It's been about an hour, so I'm going to let you all get to your weekend. But there are a few things I wanted to remind you of before we bounce out of here, which is eBPF Summit is coming right up. If you have not registered, you got to do it. And actually, let's just all go there together real quick. If you go to ebpf.io, right up here at the top, it'll have a register now. And you can go through and join our Summit Slack, and you can register with us. We have so many incredible featured speakers, and it would be great to have you with us and have you, paying attention to these amazing folks and sharing their information with us, right? So we have Brendan Gregg talking. We have Jana Dogan talking. Liz Rice will be doing how to create a load balancer from scratch. We have Daniel Borkman. Tabitha Sable will be helping us with a project that has not yet been announced, but will soon be coming. So if you register, you'll get notified of that. Dave Thaler from Microsoft talking about eBPF on Windows. Lots of really great content. The agenda, I believe, is defined here. And so here we can actually see what it looks like the agenda's up. So we can see who's going to be talking about what's happening there, all that good stuff. Have a lot of amazing speakers. We have Jed Salazar talking. Natalia will be presenting. Just so many amazing folks. So if you haven't already registered, please register and come join us. I will be co-hosting this event with Liz Rice and Thomas Graff. And so if you're interested in this stuff, it's coming right up. Definitely come check it out and join us. It'll be happening Wednesday and Thursday, August 18th and 19th, and it should be super great. Yeah, that was interesting outcome. Thank you, Russell. Good to see you, Magno. And that's what I wanted to remind you of. Go ahead and register. There's lots of stuff happening, and I will see you in 2 weeks where we will go over this amazing project. Nova. If you want to study ahead of time, there it is, the double slit experiment. So in 2 weeks, I'm going to be at Chris's house. We're going to be co-hosting. It'll be really a lot of fun. I don't know if you've seen us interact before, but this is talking about Linux telemetry. You can dig into what the application looks like and how it works. And actually, before I bounce, I'm gonna bounce, and we'll talk about this in the episode that comes up. But feel free to check this program out. I'll be covering it in 2 weeks with Chris live right here on this channel. Thank you very, very much, and it's good to see you too, Reiko. I'll see you all next time. Thank you for joining.